In physics, we're going to be looking at a lot of relationships between real variables. We'll be looking at the relationship between movement and displacement and how far something actually travels. We'll be looking at the relationships between forces and things like gravity, things like acceleration. And when we look at these things, we want to be able to investigate these concepts. We want to be able to take data and create an actual equation. How is this done? This is something that I always wondered for years. When I first took physics, I didn't get to learn this stuff, but I actually wondered, how do you craft an equation like this that represents real variables? Well, it's done very simply by graphing those variables. So remember, if we have a graph here, and this is a terrible graph, I know, just take a gander. If we have this slope right here, there are a few things we can gather out of that. The first one is the equation of a line, that y equals mx plus b. Okay? That's going to come in handy, and we're going to look at that more in just a minute. The second thing we can look at, number 2, let's put a 2, let's put a 3. The second thing that we're going to look at is the slope of that line. Now, there is an equation for the slope of a straight line, right? That's just going to be that slope, that's going to be m equals the change in y over the change in x. Now, you may not know this, but this is one of the fundamental ideas in calculus. In calculus, we want to be able to find the slope of many different functions. And so this right here, what you're doing when you're finding the slope of a line is you're finding the derivative. Now, we won't get anywhere too complex with this, but we will use this a little bit. We'll use derivatives a little bit. The third thing that we can get out of a line is the fact that there is an area under this curve. This curve has area, and so we can look at that area. Now, we're not going to deal with too complex of shapes here. We'll basically be using a triangle or a rectangle, but when we have the area of a triangle, the area here, that would be 1/2 base times height, right? Well, in this case, what's my base? My base is my x-plane. What's my height? Well, that's my y. And so I could say the area under that curve is 1/2 x times y. This is what's known as an integral. Those are the fundamental bases of calculus. These two ideas, just being able to look at the area under a curve and the slope of a curve as those curves might change. So how is this going to come in handy for us? Well, we can use this to take data, and if we can get our data into a straight line, boom, we have an equation right there. So if we can make our data fit a straight line, we have a usable equation. Let's look at what that looks like. And let's use the ideal gas law. The ideal gas law is PV equals nRT. Well, if I wanted to look at this, if I wanted to look at the relationship just starting between pressure and volume, what I would see, let's actually go to a graphing calculator to look at this. So let's use my favorite graphing calculator, Desmos. Desmos is an online platform. You can find it by going to desmos.com/calculator. And this is a very useful graphing calculator. It'll show you all kinds of functions. You can graph equations together. You can look at them, like let's say y equals 3x. And then I want to look at y equals 4x. So I can hit both of those equations. I can see how they're related. I can see how they change over time, things like that. But I can get more complex too. I could say, well, you know what? This is actually a quadratic. Make a parabola. I can say, actually, you know what? It also has this. It also has 15x. Look at that. Maybe I go, actually, you know what? Not 3. Let's say a variable. I want to see how that's going to change. So I can give it a sliding variable, and I can say, well, as I increase my parabola, as I increase that number, what's going to happen? What happens is I decrease that number. I can come over here and look at that. So I decrease it. Whoop, suddenly it flips. Whoop. I can zoom out, zoom in, nice and simple. But let's clear those, because that's not what we're here for. What we're here for is to look at the ideal gas law. So let's type that in. PV equals nRT. And nothing happens. Well, I hit enter, and it created a slider for all of these. But R shouldn't be a slider. R is a very exact value, 0.08205. My temperature, I don't want that to be 1. I want that to be close to 300. Okay, there we go. Then number of moles, let's leave that at 1. But I still don't have anything populating here. There's no lines on this graph. That's because I don't have an x and a y. So what I want to do here is I want to say, well, I'm looking at the relationship between pressure and volume. Let's say I did an experiment where I adjusted my volume, which would mean that's my independent variable, so that would be x. So I'm going to get rid of the v, put an x. And then I looked at how my pressure would change if I adjusted that volume. And so that's going to be my dependent variable. That's going to be a y. And so let's zoom in on this line. Suddenly we get a line. And we see it takes on this very specific shape. This is what's known as an inverse relationship. So if I go back to my sketch here, if I were to graph this, I'm graphing my pressure on my y, my volume on my x, and I get this curve. We call this an inverse relationship. What this means is as volume goes up, pressure goes down. As pressure goes up, volume goes down. And so our relationship could be described algebraically using this symbol. This is the proportional symbol. Pressure is inversely proportional. If they were directly proportional, it would look like this, just like that. And I would have that between pressure and temperature, but that's not the case here. So pressure is inversely proportional to volume. Just by looking at this graph, I can see that relationship. But I want to go a step further. I don't want to use this proportional symbol. I want to be able to say equals. Well, if I want to do that, I need to linearize this graph first. And I can linearize that by taking this 1 over v and plugging it in to my x. And if I do that, if I graph instead of p versus v, I put p versus 1 over v, suddenly that line will check out. It'll turn into a straight line. And if that's the case, then I can say, well, y equals mx plus b. I can see that I start at 0, so b goes to 0. And my x, I can see that's 1 over v. So I say 1 over v times m equals, and my y is p. Well, I've just created an equation here. And I could say, take this volume, multiply it by both sides, and I get pv equals m, equals some constant. That m is going to be the value of the slope, which I can very easily find. So suddenly, I've built an equation just by starting with this relationship. But I mentioned earlier there are going to be times when that slope itself might be something special. There are going to be times where the area under the curve might be special. Let's look at a situation where that slope is going to be special, and we'll still use the ideal gas law. Let's say I've done that, and I did that with each variable, and I said I can find that there's a relationship between P and V, it's inverse. I can find that there's a relationship between pressure and temperature, it's direct, and volume versus temperature is direct. I even did the same thing with moles. Let's say I did all of that, and I said, well, I'm going to graph my pressure versus volume on my y-axis, and my number of moles times my temperature on my x-axis. And if I do that, what I end up with is I get a straight line. And if I then calculate that slope, what do you think that slope is going to be? Well, that slope would just be r, the value of the ideal gas constant. And then when I make that y equals mx plus b, well, my x variables are n and t, My m, my slope, is r. Those are going to equal my y, which is pressure times volume. There we go. I built the ideal gas law by graphing it. The value of my slope is a constant. But what about that area? That area under the curve. Let's use a force versus distance graph. If I say I'm applying a force, well, let's say I'm pushing a couch. I'm pushing a couch across the table, and I want to know how much work have I done. I keep a steady force, and I move a certain distance. So now I'm going to look at the area under this curve. The area under that curve, that's just a rectangle, so the area equals base times height. Well, the base is my distance, my height is my force. What is that going to be? Well, you don't know this yet, but force is measured in newtons, distance is measured in meters, and a newton times a meter gives me energy, which is measured in joules. If I can take the units of measurement and I can combine them in a way that creates an equation, that creates a new variable, that is an equation. And so I can say the work done on that couch is equal to distance times force, is equal to the area under that curve. Another example could be something like this. I've got the velocity of a wave, and I've got the frequency of that wave. You may remember this from chemistry. We talked about this in terms of light, but this is the same thing that's going to work on a guitar string. If I tighten the tuning peg on a string and then pluck that string again, my velocity changes, and so does my frequency. And so if I graph a line of that change, then the slope of this line would be the velocity, which is in meters per second, divided by, so times the frequency, which is, the frequency is 1 over seconds, and I would be dividing by that, so that means I'm going to cross multiply. So I would multiply this by meters per second times seconds. When I do that, my variables cancel out, and I'm left with meters. And so if I take my velocity divided by my frequency, I'm left with a wavelength. Now this wavelength would be a real concept. I could take these variables and I could measure them, and I could develop this graph, and my slope of this line would be this exact constant, this exact equation. So these are concepts that we haven't examined yet. These are concepts you may be unfamiliar with. But what you should recognize is there are 3 things we can get out of any of these equations, out of any of these graphs. The first is that equation of a line. The second is the slope, and the third is the area. Whenever we have a slope that creates a new variable, we'll do this by examining the units of our variables, or we have an area that creates a new variable, then we have a real equation that we can make use of. And our first lab is going to accomplish this. We'll be looking at the relationship between 3 variables: distance or displacement, which is going to be a change in position. We'll be looking at velocity, which is like speed, but it's a vector, and acceleration. We'll be looking at the relationship between these 3 variables as time goes on. And so we'll be graphing these, and we'll be using those graphs to make equations using the equation of a line, the slope, and the area. So keep these 3 things in mind as we do our first lab.